Such ingenious formula can be proved in a single line. Yeah, but first of all, let us see what the formula is. If bk be the kth Bernoulli number, then this sum holds. Where the sum is going from k equals to 0 to n plus 1 choose k, bk equals to 0 for n is greater than 0. Let's see if this holds true or not for some of the cases that we evaluate. Let's say when n equals to 1, let's see what happens. Sum from k equals to 0 to 1 or 2 choose k, b of k. Now let's evaluate this. So first of all, we have 2 choose 0, 1, b of 0, plus 2 choose 1 is 2, b of 1. b of 0 is 1, b of 1 is minus 1 by 2. And if you don't know these values, you can look into a video over here where I have shared how to find all the Bernoulli numbers. So this is 1 minus 1, that's 0. Okay. Now, sum from k equals to 0 when n is 2, let's say. When n is 2, this sum is sum from k equals to 0 to 2. 3 choose k, b of k. Yeah. So at 0, this is 3 choose 0, 1, b of 0. At k equals to 1, 3 choose 1 is 3, b to b 1. Plus at k equals to, this is 3 choose 2, 3, b of 3. Now let's see. b of 0 is 1, b of 1 is minus 1 by 2, b of 3 is 1 by 6. So this is 1 minus 3 by 2 plus 1 by 2, that's 0. Okay, this holds for n equals 3 as well. Let's check for n equals to 3 and then we will go on to the proof. From k equals to 0 to 3 and then 4 choose k, bk. So now 4 choose 0 is 1, b of 0, 4 choose 1 is 4, b of 1, 4 choose 2 is 6, b of 2, 4 choose 3 is 4, b of 3. That is 1 plus 4 into minus 1 by 2 plus 6 into 1 by 6, and then b of 3 is just 0. And if you want a proof of why Bernoulli numbers is 0 for the base being an odd number and odd number greater than 1, if the base of the Bernoulli number is an odd number greater than 1, then it's 0. The proof is here. Okay, so now this is 1 minus 2 plus 1 plus 0. This is just 0. Okay, so we see that this is in fact true for n equals to 1, n equals 2, n equals to 3. Yeah. Now let's try to prove this. And if you have watched my video for this summing up of the natural numbers raised to power k up to n, if you have watched this video how to do this, which I have linked over here, there I told that this is in fact equal to 1 by k plus 1 sum going from m equals to 0 to k, and then k plus 1 choose m, and then we have b of m, and then we have n plus 1 to the power k plus 1 minus m. So I said the proof, not proof, but how do we implement this in different cases, and its verification in the video which I have linked over here. Yeah. Now you see that this term over here is actually the same as the thing that we have to prove. So now this is actually the sum of kth powers up to nth term. Yeah, so this formula is for sum of kth power up to n terms. Yeah, now in this formula, if we put up to 0 terms, yeah, if we put like we want to find sum raised to power k up to 0 term, then this formula should give actually 0. Yeah, because up to 0 terms, like there won't be any terms, so that should be 0, isn't it? So now, so let us substitute n as 0, and then we can equate this with 0. What do we get? 1 by k plus 1, sum from m equals to 0 to k plus 1 by m, b of m, and if n is 0, we have 1 to the power k plus 1 minus m is equals to 0. Now 1 to the power anything is just 1, and k plus 1 is just constant, which can go to other side. So we have sum from m equals to 0 to k plus 1, not by, this is just the binomial coefficient, choose m, b of m is just 0. Now replace m by k and k by n. We have k equals to 0 to n plus 1, choose k, b of k is equals to 0. Yeah, and so we have proved this formula. Yeah, and this was such a wonderful proof. Just that we need to like consider what this formula is actually going to give us. Yeah, and once we had that this formula is just the interpretation for this, and we just substitute n at 0, and that was a logically deduction. We deduced it logically that it should in fact be 0, because there were no terms, and this in fact implied this. Now let us see quite a good implication of this formula. So quite a good implication of this formula would be okay, so over here yeah, so over here what I have is sum up to n minus 1th terms. Yeah, so basically sum of sum raised to power k up to n minus 1th term is basically sum, okay, 1 by k plus 1, and sum going from let me write it in a proper way. Okay, so 1 by k plus 1, sum going from m equals to 0 to k plus 1, choose m, Bernoulli of m, x to the power, not x, n, sorry for that, n to the power k plus 1 minus m. Okay, so now over here in this formula as well we have this coefficient, yeah, this whole coefficient, let's say whole coefficient as the thing that when like summed up, this should be 0. Yeah, this coefficient should actually be 0, because this over here is 0, and multiplying by a constant also makes it 0. So that's why let's try to add the coefficient and see if that is 0 or not. So over here the coefficient is 1 and minus 1, so 1 and minus 1 is 0. 1 minus 3 by 2, 1 by 2, 1 minus 3 by 2, 1 by 2. This is just 0, and these are the formulas for summing up to n minus 1th term. Yeah, and over here, and since these are coefficients, yeah, so I've already explained that. 1 minus 2 plus 1, 0. 1 minus 5 by 2 plus 5 by 3 minus 1 by 6, enter that in calculator, you get 0. So also add up here. So basically in the sum formulas, like maybe it looks like the magic, you know, but accidentally this show up, and if we have this sum notation, then again it's easy to prove. So yeah, I think I was just trying to show that it was beautiful to be seeing in the formula, and yeah, I hope you got that. Yeah, and yeah, this was the proof. Hope you enjoyed it. Thanks for watching, and look forward to seeing in the upcoming videos too.